Okay, we'll talk about dynamic programming today. We have already covered the algorithm. There are a bunch of other algorithms in other areas which are also based on dynamic programming. So people in communications use Viterbi algorithm. That's also based on dynamic programming. So all of us use cell phones. So the error correcting code within cell phones actually uses Viterbi algorithm, and for figuring out what exactly are the bits that were transmitted based on the error probabilities of the channel. So that's Viterbi algorithm. Then Dijkstra algorithm for figuring out shortest path in a graph. That's also based on dynamic programming. Dijkstra algorithm is taught in algorithms class in computer science department. So all of these algorithms are all instantiation of dynamic programming algorithm. So today we'll talk about linear quadratic regulator problem. How many of you have taken feedback control systems before? Few people? Okay. So if you remember in feedback control systems, I know many people have not taken it, but it's not important for those of you who have taken it. This is typically the feedback control system. So this is like a controller plus plant. This is your, let's say, output. Let me call it YT. This is my regulation signal RT, and then this is my error signal ET. So this is something that people study in the feedback control system. So you have a regulation signal, you have a negative feedback control loop, and then you get the error. The error is the difference between the regulation signal and the output of the plant, and then you have a controller plus plant system which gives you the desired output. So one of the things that you study in 3551, so I think people in chemical engineering, biomedical engineering, electrical engineering, mechanical and aerospace engineering, all of them have this class on feedback control systems. And one of the core issue that you study in that class is how do we design the controller so that this error goes to 0, okay? Let me try to be a bit more precise here. So we have I'm going to put it into two separate blocks. So one is the controller block and the other one is the plant block, and then there is a U of t here that that you want to figure out. So you are basically building this block. You're trying to figure out what should be there in this block so that this ET goes to 0 as t goes to infinity. So some of the stuff that you have studied there is using Bode plot, lead lag compensator, Nyquist plot. So there are lots of different ways of figuring out what this controller is supposed to be. And today we are going to talk about the optimization way of designing this controller C. So that's one of the famous methods where we use optimization to design this particular block is known as the LQR problem. So I have the state space xt plus 1 equals to axt plus but, and my cost function j as a function of u is summation t equals 1 to capital T or t equals to 0 to capital T xt transpose qxt plus ut transpose rut, and then I have the terminal cost xt plus 1 transpose qt plus 1 xt plus 1. This is my performance index. So you can think of the state xt as this error signal et here, and then ut is the same ut that you have as the output. And we want to find the policy pi that maps xt to ut. So I want to find the policy pi that maps xt to ut such that j of pi is minimized. So here q is positive definite, semi-definite, and r is positive definite. Okay. So let's get started. How exactly should we solve this problem? So let's define the value function at time capital T plus 1. I'm going to define it as Ct plus 1 xt plus 1, which is just the usual quadratic cost. Now what should I do at time t? So this is my terminal value function. So my terminal value function is always equal to my terminal cost. And here the terminal cost is this quadratic term in x. This qt plus 1 is also positive semi-definite. So it's a convex function. Okay. What should we do at time t? At time capital T. I have to solve two problems. One is my pi t of x capital T, and one is vt of x capital T. This is argmin of ct plus ct plus vt plus 1, and this is minimum over ut of the same thing. So I have to find the argmin and then I have to find the min. What do you think? Let's look at this particular expression. So Ct plus Vt plus 1. It's going to be a long expression. Can someone tell me what this expression is going to be? So this is my running cost and this is my terminal cost. So my terminal value function Vt plus 1 is exactly equal to Ct plus 1. So what is this cost?
X capital T transpose Q X T capital T, or just whatever's in the summation, but just the capital.
Right. What do I know about xt plus 1? So this term is actually axt plus but, right? We get it from here. So if I expand it, what do I get? This is my cost to go and the cost to go is equal to this is going to be a tedious exercise today, but in the end, the result will be very sweet. So let's go through the pain for some time. So I want to simplify it further. Let's simplify it further. Do we all agree on this expression? Does this look reasonable? So now let's start collecting the terms together. I'm going to collect the terms containing x transpose x in one place, u transpose u in another place, and then x transpose u, which is this term, as a separate term. So I have one x transpose x term here and one x transpose x term here. So I want to add it up, and I get xt transpose q plus xt plus ut transpose ut plus So finally, I was able to find out what the cost to go function looks like at time capital T. Do we all agree on this expression? Okay. Now what do I have to do? I have to minimize this expression. I have to do argmin with respect to ut, and I have to find the minimum value with respect to ut. How do I find out the argmin with respect to ut? So the first thing that I need to figure out is this a convex function with respect to ut? Yes. Why is this a convex function?
R is convex, Q
So,
is convex.
Right. R is positive definite. So this is positive definite by assumption. This is positive semi-definite. So B transpose QB, this is positive semi-definite. I add a positive definite matrix with a positive semi-definite matrix, I get a positive definite matrix. And then I have UT transpose positive definite matrix UT. So this term is convex, this term is linear in UT. It depends on xt, but I'm not looking at, for the computation of this minimum, xt is just a constant. So this is a constant, and this is just a linear function of ut. So I have a convex function and a linear function, so it's a convex function. So this is a convex function. So I can take the first derivative with respect to ut, set it equal to 0, and I am done. I get the value of argmin. So let's try to take the first derivative of this horrible expression. What's the first derivative here?
R plus B transpose, R plus B transpose Q T plus 1B times UT plus X transpose A transpose QT plus 1B.
Is this the right term? Times 2.
No, the right one, the right one.
Okay, so no 2 here, only 2 here. Okay, there seems to be a lot of objection to this expression. So who wants to object first?
I want to ask
Yeah, yeah.
you said that xt is treated as a constant, but xt is also a function of u from that.
So xt is not a function of ut. Ut is a function of xt.
But to get xt plus 1 is axt plus b times u.
This one?
The equation above.
Yeah.
The equation above. So the x is a function of u.
Xt is not a function of u. U is a function of xt, and then it leads to xt plus 1. Okay, so objection number 1. Who has the objection? Okay. What is the objection?
When you take the derivative of anything transpose positive definite matrix with itself, so A transpose positive definite A, you get 2 positive definite A.
Right. So there should be a 2 here. Any other objection?
Is R symmetric?
Which one?
Is the
It's R is positive definite, so it's by definition
is
symmetric.
R symmetric?
Yeah, because it's a positive definite matrix, so it has to be symmetric. Any other objection? No? Yeah, it's actually a transpose. So 2 B transpose QT plus 1 AXT.
Why did we change that?
Yes.
So you're taking, so you have A transpose U, it's equal to A,
Okay.
right? So that's why I have to remove that. And I have to set it equal to 0. So this 2 cancels out. And what do I get? I get UT. I'm going to make it star. So UT star is equal to minus R plus So I have negative positive definite matrix inverse, some multiplication of matrices times xt. So this is my, I'm going to rename it as K capital T. So my pi t of xt is K capital T times xt. This is known as a controller gain. Any questions? Okay. So we have fought half the battle, the other half is still left. The first half of the battle was to compute the argmin, and we have been able to compute it successfully. The second half of the battle is to compute the value. So now I have to substitute this ut star in this expression and find out what this whole expression looks like. Okay? Who wants to do that?
Well, the first part should cancel, right? Oh, no, wait, never mind, it's not that easy.
Yeah. So I'm looking for volunteers. Okay.
Can we introduce some temporary variable to make it less ugly, maybe?
Not at this moment, but we'll introduce the temporary variable in like 5 minutes later. Okay. So I have this term xt transpose this xt. So I'll keep it like this. Then I have ut transpose this times ut. This is so sad. Let me write it this way. Xt transpose kt transpose this term times kt times xt. Right? And then I have plus 2 times xt transpose A transpose qt plus 1 B kt xt. I think this looks correct. I don't think we have made any mistakes so far. So I have xt transpose something xt, xt transpose something else xt, xt transpose something times xt. Okay, so I have a bunch of matrices that I can collect together. So I'm going to write xt transpose here, and then I need to find out what's inside this big parenthesis. So I have q plus A transpose qt plus 1a, and then I need kt transpose this kt. So let's figure this thing out. What is this transpose this times this? Let's do it. So I have A transpose qt plus 1 B R plus B transpose right. So kt transpose this times kt turns out to be this, and I have a matrix inverse and a matrix right next to each other. So I get something that looks simple, at least simple enough for me to be able to write it, plus A transpose qt plus 1 B Okay. Everyone agrees with this term? Okay, we are all in agreement. And then I have to compute this term. So I have minus 2 A transpose QT plus 1 B R plus B transpose. Okay, so this is what I get. Yes. Right, so this term and this term are the same except that I have a negative 2 sign and a plus 1 sign here. So I can do the simplification. How should I simplify? Okay, I'll write it. xt transpose q plus A transpose minus okay. I think this is correct. So we found the value function as well. Do you notice something cool about this one step dynamic programming thing? So we did the dynamic programming only for the final time step, capital T. Is there a pattern? What pattern do we see here? So I look at the value function at the final time step. That's this value function. It's state transpose qt plus 1 state. I look at the value function at time t. It is state transpose a matrix. It's a symmetric matrix, by the way. Do you see it's a symmetric matrix? So this is a symmetric matrix. This is a symmetric matrix. This is a symmetric matrix. So I have a symmetric matrix here times xt. So I have xt transpose a symmetric matrix times xt. It turns out that this particular matrix is also a positive semi-definite matrix. So just like qt plus 1 here was a positive semi-definite, this particular term is also positive semi-definite. Can someone tell me why this should be positive semi-definite? The reason is this is a positive cost. For every xt, this is a positive cost. I minimize with respect to ut. I get something which still remains positive. So I have a positive function. I minimize it. The minimum point also has to be a positive number. It cannot go negative. So this is a positive, this is a non-negative function or positive function. I minimize it. I should get something that is a non-negative value. So this is greater than equal to 0. Therefore, this should also be greater than equal to 0. That's why it's a positive semi-definite matrix. So I'm going to call this matrix, I'm going to denote it by capital PT. The other thing I notice here is with my kt, so my action, my policy is actually a linear function of x. And I can compute what this matrix looks like. Okay, so let me write it down in one place. So my pi t xt equals to kt xt, and my vt of xt is equal to xt transpose pt xt. What should my pi t minus 1 xt look like? Oh, sorry, xt minus 1. So let's do the next step of the dynamic program. So that's the this is the pattern that we see, at least at time capital T. This is the pattern. I know that my pt is greater than equal to 0, and kt is a matrix that's given by this. Now, what is the cost to go at time t minus 1? It's c t minus 1 plus vt, and this is equal to xt minus 1 transpose q xt minus 1 What should my policy be? Who wants to go over all that calculation again? And come on, guys, it builds character. If you do it first time, it's an innovation. Second time onwards, it starts building character.
We take the derivative with respect to u t minus 1.
Sure.
And at the top right of the expression, it would be the same thing.
It'll be the same thing.
But ut will be replaced by ut minus 1. And
Right. So this will replace with ut minus 1. The only difference is here I had qt plus 1.
here it will be qt.
And here I will replace it with pt. So all I have to do is just replace qt plus 1 with p capital T. Okay? So we didn't get the opportunity to build our character. Too bad. So this is my kt minus 1, xt minus 1. Okay, so I was able to find the policy. Now what about the value function? I have to do the same thing. I have to replace qt plus 1 with p capital T, and I get the value function as well. So this would be xt minus 1 transpose q plus a transpose pta minus a transpose ptb Now it doesn't look that bad. Okay, so the first time it was very difficult. We had to go through all this computation. But second time onwards, because we are students of principle of mathematical induction, we just use that hammer and we get the value function and the policy for all time steps. Any questions?
And that's where we get linear quadratic from?
That's right. So you get, so there are two reasons why people call it linear quadratic. One is because the state transition function is linear and the cost is quadratic. And then the optimal policy is linear and the optimal value function is quadratic. So it's L square Q square R problem, but we just call it LQR, okay, for brevity. Okay, so LQR is another way to design this control policy C here, which maps ET, the error signal, to UT. And you know, if you go back to your your class on feedback control systems, you will realize that once you were, remember you were picking a k value and then the Bode plot was moving in some random directions and it was a complicated stuff. So this k that you see here is the same k that you see in the Bode plot, okay, when you were plotting that k in the Bode plot, except that in those problems it was a system where everything was scalar, the error signal was scalar, the u signal was scalar, y was scalar, everything was scalar. Now we can do it for the vector valued state, action, space, but the cost function here is quadratic. That's the only difference. Now you can pick whatever cost function you want and you can still solve the problem, but the good thing with the linear quadratic problem here is that you can compute everything in closed form. So you get everything in closed form expression, and this is the optimal solution. And there is no other optimal solution to this particular problem because it's all convex, strictly convex problem. So let's try to write down what is known as a Riccati equation. So this is my Pt minus 1. And this is known as a Riccati equation. Pt equals to Q plus A transpose Pt plus 1A minus and so we get that pi t of xt is given by kt of xt, kt times xt, and this matrix kt is given by and then value function is given by this. Proof by induction. Any questions so far? No questions? Okay.
Question, maybe.
Yes.
The PT plus 1, does that imply that there's some sort of non-causality? We're looking ahead a time step?
So dynamic programming is always solved backwards. You start with capital T, then T minus 1, then T minus 2, and so on.
Okay.
So that's why you start with PT. So P capital T plus 1 is initialized at Q capital T plus 1. And then you go through this recursion and you get the policy which requires PT plus 1, and then you get the value function which requires P cap PT. Any other question? Okay. So now I want to add a small twist to this particular problem. I want to add a state action constraint. And I want to see what we can do to solve this particular problem. Let's say I'm going to add the following constraints. I want my xt less than equal to r square for all r, or maybe xt is at is less than equal to xt is less than equal to bt. Suppose we have a constraint like this. So this is a state constraint, and then we have a constraint like this, gtxt plus htut plus, I don't know, dt equals to 0 or greater than equal to 0. No, less than equal to 0. Suppose I have constraints like these. How will we incorporate these constraints within this system? If you remember going back to those classes, the feedback controls class, remember we used to talk about, I know I have not taught you, but I've taught 3551 before. We talk about the upper bound on the error, the settling time, the rise time, all that stuff, right? So a lot of those constraints can be written in this particular way, okay? So rise time constraints, settling time constraints, all of that can be written in the form of these constraints. So now I want to solve the dynamic programming problem with these constraints. How do we solve it?
Those first two are convex sets.
These are all convex sets, yeah. This should be not for all r, sorry, for all t, for all t, for all t. So I want to minimize pi t xt equals to argmin ct plus vt plus 1. What constraint should I put here? Can someone tell me what are the constraints here? So this is the cost function I want to minimize. I'm minimizing over all ut. What are the constraints? Suppose these are the three constraints I have. Yes?
Only the third constraint because xt is not an minimizer, right?
That's true, but think a little bit more deeply. This should hold for all time t. So xt, so ut doesn't influence xt, but ut influences xt plus 1. So we need to put the constraint for xt plus 1 here. Okay? So I have AT less than equal to xt plus 1, sorry. I have GT, sorry, I'm writing AT plus 1 less than equal to xt plus 1 less than equal to BT plus 1, GTXT plus HTUT plus TT less than equal to 0, and then xt plus 1 R square. Okay, so you have to collect all the constraints. So the constraints were given in this particular form. Now I have to collect all the constraints that are influenced by UT. So the constraint of xt is not influenced by UT, but xt plus 1 is influenced by UT. So I have to collect all those constraints and write it down. How do I solve this problem? Now we can no longer do this business. I have to find out the Lagrange multipliers corresponding to all of these inequality constraints. Now, I guess this is a quadratic cost. This is a quadratic cost. The constraints are linear. So I can use quad prog, right? I can use quad prog to solve this problem. And I can get pi t and I can get V capital T x t by finding out what the minimum value is. What will this be? What will this function look like? So it turns out that Vt is no longer a quadratic function, it's just a convex function. Okay? So this will be a convex function of xt. The proof is somewhat complicated because you are taking a minimum of a function with bunch of constraints. So the proof is very complicated, but Vt will be a convex function of xt. So you will at least retain the convexity, but you no longer retain the quadratic function. So actually, very soon you will have to write either the sequential quadratic programming or method of multipliers approach to solve this problem for every value of xt. And that makes it very complicated. So whenever you have a constraint, so as long as you are in an unconstrained setting, everything is very simple and straightforward. As soon as you get into the constraint setting, even if you have a simple state constraint, it becomes very complicated. So when you are driving a vehicle, you have a lot of constraints. You have speed limit constraint, that's a state constraint. You have distance with the vehicle in front, that's a state constraint. You have jerk constraints. You know what jerk is? Jerk is rate of change of acceleration. Okay, so you have jerk constraints on the vehicle because you don't want the riders to feel spooked out. So you want to make sure that you don't accelerate and decelerate with very high change in acceleration or deceleration. So that's called jerk. So you have jerk constraint, which is constraints of this type. So ut minus 1 should be less than equal to epsilon minus epsilon. So the acceleration at time t minus the acceleration at time t minus 1 should be upper and lower bounded by some small number. So this is known as a jerk constraint, and so then the problem becomes even more complicated. Now you have to keep track of what ut minus 1 was. So that becomes part of the state space. So these are the usual ways by which you can create problems that are more complicated than what you had imagined. Solving them becomes even more complicated because now you have to do all this backward computation business. So how do you solve these kind of problems? I mean, we know that jerk constraint is real. We don't want to sit in a vehicle where the driver is, I don't know, like driving like there is no tomorrow. We have all been in such Uber vehicles where there is no tomorrow, you know. So we don't want to be in those Uber vehicles. So how should we go about solving this problem? It's a problem that needs to be solved. So how do we solve it? There are a bunch of autonomous driving companies that are solving problems of this type on a day-to-day basis. So the way to solve it is as follows. Where should I write it? There are a bunch of approximations, so you can't really solve it exactly, you have to solve it approximately, and that leads to an area called approximate dynamic programming. So in approximate dynamic programming, the goal is that we have a complicated system equation, we have a complicated cost function, we have complicated constraints. So how do we solve that problem? So we can either simplify the model, so we do what is known as a model approximation. So by model approximation, what I mean is I approximate this particular dynamical model of the system. So I start with a nonlinear model and maybe I linearize that model around the equilibrium point. So that's a model approximation. You can do cost function approximation. So I have some complicated cost function, but I'm going to just consider some simplified cost function in that case. Then you can have approximation of the value function and the policy function. So that's known as, so reinforcement learning, for instance, is of that type where you approximate the value function and the policy function using neural network or some other kind of function approximator. So these are the things we'll be talking about. You can do look ahead approximation. So instead of solving the problem all the way up to capital T plus 1, so in the rocket example, capital T was 1.8 million, so we can't really solve 1.8 million time horizon problem. So we'll just look at 10 or 15 or 20 time steps at a time. So that's a look ahead approximation. And then you can also do approximate optimization. So I know that I have to solve this problem, but instead of taking 1 million method of multiplier steps in order to solve this problem exactly, I'm just going to take 5 method of multiplier steps and solve this problem. Okay, so that's an approximation in the optimization itself. So in the subsequent classes, starting from next week Friday, we'll talk about what kind of approximation methodologies are there. I'll give you some examples. Of course, the subject of approximate dynamic programming is huge. One of the main contributor to this area, he's coming as a seminar speaker in ISE department next week on Tuesday and Wednesday. So I highly encourage you to go for his talk. It'll be in Baker Systems, somewhere 198, I think, 198. So this is 188. I think the room is somewhere here. So on Wednesday, 4 to 5 p.m., he's giving a talk. So I highly encourage you to go for that particular talk. So I'll give you different examples of all of these approximations, and then we'll end the course on whatever, 25th November or something. So thank you so much. I'll see you on Wednesday next week for your midterm. Midterm syllabus is Lagrange multiplier theorem, all the stuff we did since then, contraction mapping theorem, blah, blah, blah. It doesn't include the dynamic programming and dynamic optimization stuff that we have talked about. The assignment 6 on dynamic optimization has been uploaded, but it is due 2 weeks from now. So you have some time to think about it. And that's pretty much it. Good luck with your midterm preparations.